Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Okay, so good morning, everyone. My name is Adrian. I'm a PhD student at the Microsoft Research INRIA Center and also in the LEAR team led by Cordelia. And I'm going to present you two recent papers about learning temporal information for action recognition in videos. This is all joint work with Zaid Arshawi and Cordelia Schmidt. So there's going to be two parts. The first part is about Actom Sequence Models for efficient action detection. So what's the problem? The problem here is you want to find if and when an action is performed in a video. So we're interested in short human actions like sitting down. So basically a few seconds. And we want to detect them in a long unsegmented stream of frames. So long unsegmented video sequences like several hours of movie data, for instance. And so what we're doing exactly is called temporal detection, that is find short clips that contain the action. And the approach we propose is to model actions as sequences of action atoms that I called actoms in the paper. So what are actoms? They're atomic action units. Put it in another way, they are action-specific short key events whose sequence is characteristic of the action. So here, for instance, you have an example of three Actom annotations, of two Actom annotations, one for the action opening door from the Forrest Gump movie, and another for sitting down. So by action-specific, I mean they are semantically meaningful. So we obtain these annotations at training time only from annotators. And so there are sub-events that make sense for people. And so they are specific to the action, right? There's not much meaning shared between opening door and sitting down here. And also what's important is their sequential aspect, right? So it's their sequence that is characteristic. If you just look at the middle one, it's unclear what Forrest Gump is doing. And if you look at the other way around, it seems like he's closing the door instead of opening the door. And that's really important when you do detection because you have a chance level of 0.001%. So this kind of confusion happens all the time. So you need the sequential aspect. And so what we do is we propose a simple model that's called this Actom Sequence Model. So we model each actom using an extension of bag of features. So we propose to use an histogram of time-weighted quantized spatio-temporal interest points. So basically we just have like local motion information and we make each point vote for a particular actom or sub-event. And its importance for this sub-event is weighted by how far it is from the focal point of these sub-events. Okay? So then we can just concatenate the per actom histograms and we get this one long sparse sequentially structured model that encodes soft ordering constraints between actions. So I'm going to go a bit fast for this first part. So I won't go into the details of the parameterization of this model. But basically now when you have built this model of actions, you can learn a classifier, right? So you take your favorite classifier. Mine is SVMs. Basically what matters is that this classifier, it outputs a posterior probability of an action knowing its actoms. So knowing its temporal structure, okay? But we're not done yet because at test time, we don't know the actoms. We don't know the temporal structure. We just have this unstructured stream of frames. So what we propose to do is to use the training actoms to learn actom candidates, right? And we fit a simple non-parametric model, basically, to learn this temporal structure distribution. And what we do is we use this distribution over inter-actom spacings as a prior on temporal structure, okay? And I'm going to show how we use this prior for detection. But just to give you a hint of what is this temporal distribution that we learn, this is for the smoking action. You see here this discrete distribution that we learn, ordered by probability. So this is the estimated prior probability. And if you look at the fifth most likely action, it has two actoms, which are quite short and quite close to each other, and a third part of the action, which is flatter and further away. And basically, this captures a way of performing the smoking action in movies where people smoke with style. So they bring the cigarettes to the lips, smoke, and blow slowly away. So this is one of the styles that we capture, basically. Okay, so basically now you have two things. You can compute the posterior probability of an action knowing its temporal structure, and you have this prior. So for detection, we estimate the probability of an action being centered at a particular frame by just marginalizing over this prior. Okay? So very simple. But what this allows you to do is to do a sliding central frame detection approach. So it's like sliding window, but you don't have windows. You just evaluate this probability every n frame, and you don't have to choose multiple scales or have multi-scale sampling heuristics like people do for sliding windows. They are captured by your prior. And so in our conclusions, using this prior helps a lot. And you can also use it for sliding window. So if you're doing sliding window, instead of having multiple scales and then doing non-maximal suppression like usual, learn a prior over your scales and marginalize. It robustifies a lot the performance. So I can show you one quick example. What can you do when you can detect actions? You can do an action summary. So this is the Coffee and Cigarettes movie, and it's going to play in fast forward, except when the system automatically detects drinking action, where it's going to be played in slow motion. So it's too small for you to see, but here you have like the probability score also on top. And so basically this is an automatically generated movie summary that's oriented toward one particular action.
If your probabilities don't use logistic regressions of SVM?
You can use logistic regressions, totally. That's something that a lot of people say. That's exactly true. You can. The thing is that logistic regression is a bit similar to SVM in the sense that both use. So logistic regression is not a probabilistic model. It just uses a sigmoid. It just uses a sigmoid as a model for probabilities. And if you look at how SVM probability outputs are made, it's the same thing. It's just the difference is that for SVMs, the training is in two stages. You fit the SVM, then you fit a sigmoid. Logistic regression fits everything together at once. That's
my understanding is that the regression was a probabilistic model.
Yeah, it outputs something like probabilities.
No, my understanding it was a probabilistic model.
Yeah. It is. No. You are right. It's just it uses a sigmoid as probability model, and SVMs use sigmoids also. But you're absolutely right. Okay, so just to conclude this first part, I'm not going to present quantitative results. It's all in this paper. 5 minutes? No. Okay, good. So the conclusion is that ASM is an efficient model of actions with a flexible sequence of key semantic sub-actions. So these actoms, what was interesting is that they're semantically meaningful, but we're not sure they would be discriminative. And actually they are, so that's interesting. And it leads us, and it gives us also like meanings to interpret basically decompositions. Also, we saw that the sliding central frame approach is a principled way to do multi-scale detection using this prior and temporal structure. And in our experiments, we show it outperforms a bag of features, the rigid temporal structured extensions of bag of features, and state-of-the-art methods, including those using tracking. We don't use tracker here, but we could use it to boost performance. Okay, so this second part is about comparing the dynamics of actions. So here the problem is different. It's more like the traditional classification problem. So we have clips of short duration, and we are asked the question, is there this action, are people falling in there, yes or no? Okay, so it's classification and detection anymore here. And what we want to do here is to define a good similarity, or a good kernel, between videos that can compare videos, right? And so far, the state of the art is bag of features. And for videos, you can view bag of features as computing per frame bag of features and then averaging them, okay? So basically, right now, what people do and what works best on this kind of realistic data is to compare histograms over averaging over frames and using standard kernels on histograms, like intersection kernel or whatever. And here what we want to do is say, okay, this works really well. This captures a lot of information. We don't want to make a silver bullet that's going to replace this, but we want to make something complementary to it, okay? And one thing that is not captured by bag of features and is averaging statistics is kind of first-order moment statistics, which are just how frames relate to each other through time. So these temporal dependencies. And so how we propose to do that? We propose to model actions as time series of frames, okay? And what we're going to do, and what I'm going to show now, is a time series kernel that can compare the dynamics of two time series, okay? And the core part of this kernel is autocorrelations. So each time series has its dynamics modeled by its autocorrelations. So one point to understand is that cross-correlation is something that's used a lot. All these template matching methods with cross-correlation, there are similar things for videos, but it's different, right? They're cross-correlating, they're computing an alignment score between two sequences. Here, we're using autocorrelation per time series, and we're comparing two autocorrelations, okay? So modeling actions as time series is also something quite well known in speech, gesture recognition. But here, in general, it's more like dynamic probabilistic models, like hidden Markov models or things like that. So we're differing from that. And we're also differing from kernels on time series, which, for instance, are based on dynamic time warping. So they compute alignments. We compare dynamics and don't compare alignments. Okay, so just a quick slide about how we represent our videos. So I said actions as time series of frames. We extract the features Cordelia mentioned, these dense tracklets, dense short point tracks from dense optical flow, compute motion boundary histograms. And what we do is we count visual words associated to those tracklets for each frame. So we build a histogram. Yes?
What did you mean by first order then? Can you just be a bit more precise about it?
Yes, I will show you actually, in the definition of autocorrelation, this will be clear, but it just means, yeah, the dependencies, like the covariance if you want, some kind of covariance. In this case, it's autocovariance. Okay, so basically you just have, sorry for the many basicallys, you have a time series of bag of features. Each frame is represented as a bag of features, but it doesn't really matter. You could use the awesome pause estimation we've seen before and have a tree representing every frame. What I will show you only needs one thing. It needs a basic mean to compare two frames. So here, as there are histograms, we're using basic kernel on histograms, using intersection kernel, but you could use anything you want. Okay, so we represent the dynamics of one action, so of one time series, using its autocorrelation operator. Okay, what is the autocorrelation operator? It's the normalized cross-covariance between a time series, okay, and a shifted version of itself. So it's the same time series, but just shifted by a certain number of frames. This is the normalization term, and this is the autocovariance matrix. So this is where the first order terms appear. Okay? But they are dependent on the time. Okay, and so what does this thing measures? So I say operator, it's basically, it's a matrix, but it can be potentially of infinite number of dimensions. It depends on your basic kernel, okay? So it's an operator. And this operator, or matrix if you like, measures the statistical dependencies between frames. So one simple way now that we model the dynamics of a time series with this autocorrelation operator, we can compare two time series by comparing their autocorrelations, their respective autocorrelations. So here we can use standard Gaussian RBF kernel with base distance that's called the Dako distance for the difference of autocorrelation operators. This is the natural distance, basically, in the space where these operators live. It's the Hilbert-Schmidt norm. Just think of it as an extension of the Frobenius norm. Okay? Okay, so one thing that's interesting is that this kernel, it works for series with different durations, periodic or not. Okay? So it works in very general, in many cases. However, the problem is that estimating this distance, okay, has a computational complexity that is cubic, but in the dimension of the frame feature space, okay? So we have this kernel on base frames. To this kernel corresponds a frame feature space, okay? That can be infinite dimensional. And this the complexity of evaluating the distance is cubic in the dimension of this space. So basically it's intractable. We cannot compute it. Just to compare two videos, okay? But there's a solution, and it's a classical application of the kernel trick. So basically we're going to write a dual expression of this distance. And after rolling the computations, what you can see is that this distance can be expressed as a trace of products of various matrices. Okay? I won't go into the definition of these matrices, but what matters is that they can all be expressed with this big K, capital K matrix, which is the kernel matrix of the evaluation of all pairs of frames. Okay? So it's also called the self-similarity matrices. It's the between frame similarity matrix. And this, evaluating this distance now, is still cubic. Damn it. No, it's cubic now, but in the number of frames, okay? And as we deal with short actions, like something like 100 frames, this takes on the order of milliseconds, okay? In Python. So it's fast. Okay, so I mentioned that this kernel can be expressed in function of just one matrix, which is this K matrix, this matrix of similarity between frames. And here you can see that this relates to something that is very well known in action recognition, but also in other fields. It's called the self-similarity matrices. Okay, it was studied, a long time ago for periodic actions, etc. And so here you have two actions that are the same action, so it's a bit small. So it's two rugby ball kicking actions, different actions. And here this big K matrix, right? So this is the similarity of all frames from the first action, the similarity between all frames of the second, and these are the cross similarities. Okay, so here you have frames and frames. And what you can observe, it's pretty obvious, I think, is that these two matrices, they show remarkably similar patterns, right? So this is not something new. This is something that is, again, known. For instance, Ivan did work on this. And for instance, what Ivan did is saying, okay, let's view these as two images. They're remarkably similar and to us as humans. So let's view them as images. Let's take hog features on them and compare hog features, okay? Computer vision view of things, okay? It works really well. And here, basically, what we show is that this is related to the autocorrelation operator of the time series, okay? So it provides some mathematical background to the self-similarity matrices. And here's for different actions, you see it's much less structured. Okay. So like I said at the beginning, our goal is not to make silver bullets and overcome the emperor bag of features. It's just to complement it. Okay. And so what we want to do is combine our DACO kernel, our dynamics kernel, with an averaging kernel. So we use a bag of features kernel. Not exactly bag of features, called difference of mean elements. I didn't find it published anywhere before. It's just bag of features, but in the frame feature space instead of the input space. So subtle difference, but it boosts performance a little bit. And it can be expressed also just in function of k. So you have it basically for the same, with the same operation. And here you have the accuracy in % on 3 action recognition benchmarks. So simple one, KTH, more difficult one, UCF Sports, really difficult one, YouTube. And what we wanted, so it seems that in all cases, almost, averaging works best compared to our dynamics. But we're just comparing actions based on how their frames relate to each other, right? So it was expected. However, also what was expected and what's good is that the combination of these two kernels, the averaging one and our dependency kernel, improves performance, okay? So we have also now like a bit more experiments and a bit better results than this since then. Okay, so to conclude the second part, what I showed here is that you can use autocorrelation to represent temporal dependencies. And this is a principled way of extracting information from self-similarity matrices. Okay. We also showed what we wanted at first, that dynamics are complementary to average statistics. And for future work, so it's quite preliminary, so there's lots of stuff that you can do. For instance, you view actions as time series of frames. This is a kind of a signal, a multivariate signal. What are its properties that are useful? Is like, for instance, smoothness important? Right now, with bag of features, it's absolutely not smooth. Maybe using Fisher vectors would improve. Also, we have to make some assumptions to make the computations possible. Like most time series paper, we assume stationarity. This is violated in our case, but maybe we can make a local version of our kernel or a windowed version to account for this assumption. Also, there are like a variety of parameters that need to be investigated. This was published at last year's BMVC, actually, if you want more details. And just to conclude this presentation, a few take-home messages. Basically, what I showed is how to leverage temporal information for action recognition. First part was to learn a model as a sequence of temporal parts. The second part was to compare these temporal dependencies. And what I want to highlight is basically that time is not space. So I should add in digital videos, okay? Because in real world, maybe it's true in our brain, etc. But in digital videos, really, time is not space. That's at least quantitatively true. I think everyone would agree. The difference between two neighboring frames is much bigger than the difference between two neighboring pixels. And my personal belief is that it's also quantitatively true, because time is sequential by nature. It goes into one direction only. And I believe, and that's what I've tried to do in my PhD, is to use this distinction in order to improve action recognition. And I think I've shown a few ways to exploit this. And also another take-home message is that when dealing with real-world videos, I haven't shown a lot of videos because I don't have a lot of time, but you can look on my website. There are lots of videos. When you're dealing with real-world videos, you want to make structured models in order to be able to predict more complex activities, right? So use more information. But when you use more information, more structure, you make more assumptions, necessarily, okay? And the thing is that in real-world videos, these assumptions are likely to be violated. So whenever you have to make a model, and a big part of my work, especially on the first part, was to make the model robust to the violation of these assumptions. So it's really crucial to account for this. Thank you very much. Yes?
Time for one short question. Oh, good. So, is there a very natural way of comparing these autocorrelation parameters? Because actually, your autocorrelation parameters are the sufficient statistics for learning the autoregressive model for that.
Exactly.
Data. So what you could do is take the when you're comparing two models, you take the whole family of models that you would simulate under one set of parameters, calculate their likelihood under the other model, and take an expectation. And that would give you a, because taking just like L2 norm between autocorrelation is not convincing.
You're absolutely right. This makes a lot of sense. Also related to your question, we've tried something else that's not here. So this is related to autoregressive, so ARMA models, but not exactly the same. We tried also fitting ARMA models and comparing the models also. This seems to work equivalently, but it's very preliminary results. So, but we are definitely working in this direction. It's very interesting. Thank you.